Every time you charge your smartphone, every time your laptop fan spins up, sounding like a jet engine preparing for takeoff, and every time a massive data center in Virginia consumes enough electricity to power a small city, you are witnessing a fundamental law of physics in action. We call it waste heat. It's annoying. It burns your thighs when you hold your laptop. It drains your battery. But physicists call it something else. They call it the Landauer limit. It is the thermodynamic price we pay for erasing information. When your computer processes data, when it calculates a spreadsheet, renders a video game frame, or trains a neural network, it is constantly manipulating bits. It turns O south into 1 south and 1 south into O south billions of times per second. And crucially, it discards old information to make room for new information. This act of discarding, of erasing, is what generates heat. It is a thermodynamic tax levied by the universe itself. And for decades, we accepted this tax as inevitable. We built bigger fans, massive liquid cooling systems, and we even located server farms in the Arctic Circle just to keep our machines from melting down. But what if we were wrong? What if the heat isn't a necessary byproduct of computation, but a symptom of bad design? What if we could build a computer that consumes almost zero energy? A computer that runs cold? This isn't science fiction or perpetual motion magic. It is a rigorous field of physics and computer science called reversible computing. And if we can make it work at scale, it will change everything from the battery life of your phone to the sustainability of the entire AI revolution. To understand why our computers burn so much energy, we have to look deep inside the silicon at the logic gates they are made of. The most basic building block of a modern CPU is the NAND gate, or the AND gate. Let's look at a standard AND gate to see the problem. It takes two inputs, let's call them A and B, and it produces one output. E vai and b da output is e vai 0 and b da output is 0, simple enough. But here's the problem. If I cover the inputs and just tell you the output is 0, can you tell me what the inputs were? Current computers are, by definition, irreversible. They are designed to destroy information billions of times per second. Every time a register is overwritten, every time a logic gate resolves, heat is generated. They are entropy machines. They are essentially electric heaters that also happen to do math. But in 1973, another IBM physicist, Shotles Bennett, realized something profound that challenged Landauer's bleak outlook. He reasoned that if we could design a computer that never erases information, a computer where every logical operation preserves the input data so it can be run backwards to retrieve the inputs, then theoretically we could bypass the Landauer limit completely. We wouldn't have to pay the thermodynamic tax. We could process data essentially for free, logically speaking, recycling the energy instead of dissipating it as waste heat. This is the dream of reversible computing. Imagine a pendulum swinging back and forth in a perfect vacuum. If there is no air resistance and no friction at the pivot, it swings forever. It converts potential energy into kinetic energy and back again perfectly without loss. Reversible computing tries to do the exact same thing with logic and electrons. Instead of standard logic gates that lose information, we use specialized reversible gates, like the Fredkin gate or the Toffoli gate. A Fredkin gate is a controlled swap gate. It takes 3 inputs and gives 3 outputs. It preserves all the information. If you know the outputs, you can always mathematically reconstruct the inputs. This means you can run the computation forward to get the answer, print it out, and then run the computation backward to return the computer to its exact initial state, recovering all the energy invested in the process. It is often called adiabatic computing, referring to a thermodynamic process where no heat is transferred. So, the obvious question is, why aren't we using this yet? Why is my laptop still hot? Why isn't my phone battery lasting a month? The answer is friction. Not mechanical friction, but electrical resistance. In the real world, we don't have perfect vacuums or perfect wires. Wires have resistance. Transistors leak current. Even if the logic is perfectly reversible, The physical hardware is imperfect. Moving electrons around costs energy because they bump into atoms. However, the potential gains are so massive that research is accelerating rapidly. As we approach the end of Moore's law, we can't just keep making transistors smaller to make them efficient. They are getting too dense and too hot. We are hitting the thermal wall. If we want computers to get thousands of times faster than they are today to simulate folding proteins or model whole brains, we physically cannot do it with irreversible logic. The chips would vaporize instantly. Reversible computing is not just a cool theoretical idea. It might be the only path forward for high-performance computing in the post-silicon era. The implications are staggering. Think about AI. But building a reversible computer is incredibly hard. It requires a complete rethink of everything, all the way down to how we program. Our current programming languages, Python, Java, C++ are irreversible by nature. When you write x equals 5, you are destroying whatever value x had before. That destruction generates heat. In a reversible language like the experimental language, Janus, you can't just overwrite variables. You have to swap them, or use special operators that preserve history. You have to manage the garbage data, the history of the computation, and uncompute it to clean up memory. Debugging a reversible program is a trippy experience. You can literally hit a reverse button and watch the code execute backwards, line by line, undoing its actions, restoring variables to their previous states. It turns the concept of time in software into a spatial dimension that you can traverse in both directions. There is also a fascinating and critical connection to quantum computing. Quantum computers are, by the laws of quantum mechanics, inherently reversible. Quantum gates' unitary transformations must be reversible to maintain the quantum state superposition without collapsing it. If a quantum computer lost information during calculation, it would decohere and fail. So, the massive investment into quantum algorithms is actually helping us understand how to build reversible classical computers. We are learning how to compute without destroying. We are rediscovering the physics of logic. One of the most promising physical implementations for this involves superconducting logic. Using materials that have zero electrical resistance at very low temperatures near absolute zero. Combined with reversible logic gates, researchers have built prototype chips that consume practically zero energy. The energy simply sloshes back and forth like water in a tank, doing work without being lost to resistance. The challenge is, of course, the cryogen. Keeping chips that cold is expensive. But even with the cooling costs for massive supercomputers or data centers, the efficiency gains of the computation itself could be revolutionary. It effectively moves the energy cost from the chip to the refrigerator, which is much easier to manage. Another approach is ballistic computing. This is where it gets really Imagine a computer where the bits are represented not by voltage levels, but by actual particles or packets of electrons firing through tracks like a complex billiard ball machine. If the tracks are frictionless and the collisions are perfectly elastic, bouncing off without losing speed, the computation happens without energy loss. It sounds like a steampunk fantasy, but nano-engineers are working on electronic versions of this, using fluxins or single electrons. We are currently at a crossroads in technological history. The demand for compute is growing exponentially. AI, crypto mining, the metaverse, scientific simulation, it all needs more power. But our energy production is linear. We cannot just build more nuclear power plants forever to feed the AI gods. We have to make the compute itself efficient. The current paradigm of destroying information to calculate is a brute force approach that served us well for 70 years, but it is reaching its physical limits. Reversible computing offers a way out. It suggests that intelligence doesn't have to be hot. It suggests that thought can be thermodynamically free. The transition won't be easy. It won't happen overnight. It will require new chips, new languages, and a new generation of engineers who understand the thermodynamics of information. It requires unlearning decades of wasteful programming habits. But the prize is a world where computation is ubiquitous and essentially free in terms of energy. A world where a smart contact lens doesn't need to be charged every night. A world where we can simulate climate models with atom-level precision without boiling the oceans to run the simulation. For the average user, this revolution will be invisible. You won't see the reversible gates. You will just notice that your phone lasts a week instead of a day. You will notice your laptop is sleek, fanless, and silent. But for civilization as a whole, it is a leap comparable to the invention of the transistor itself. It is the shift from the steam engine era of computing loud, hot, inefficient, to something far more elegant and sustainable. If you are a student, a developer, or just a futurist, keep your eye on this field. Look for terms like adiabatic circuits, reversible logic, and Landauer limit. The future is not just faster. The future is reversible. And unlike the entropy of the universe, which only moves one way, in the world of logic, we might actually be able to turn back time. If this deep dive into the physics of information sparked your curiosity, make sure you are subscribed to the channel. We don't just cover the gadgets. We cover the fundamental science that makes them possible. We explored the limits of physics and engineering. Understanding the limits of technology is the first step to breaking them. See you in the next one. And remember, you can't unwatch this video, but you can rewatch it.